In this video, we're going to take a look at electron configurations, what they are, and how to write them. So an electron configuration is basically the same as our orbital diagrams that we saw in our last video. But in this case, it is simply a listing of the electrons in order of increasing energy from left to right. So it's a listing of electrons, what orbitals they're in, and how many electrons are in those total orbitals. So let's take example aluminum. Aluminum has 13 electrons total. Okay, we're just talking about its atoms, so we're not talking about any ions. So we've just got 13 electrons. And if we go in order of filling them, there are 2 electrons in the 1s orbital. So the way we represent that is we write 1s, and then we use a superscript of 2 to denote that there are 2 electrons in there. The next one filled is 2s, and again, there are 2 electrons in there. The next sub-level that we fill are 2p's. Now, instead of writing out 2px, 2py, 2pz, we're just combining them all together to write just 2p, and there are 6 electrons total, 2 in each of the different p orbitals. Continuing on, we fill 3s next with 2 electrons, and that is 6, 7, 8, 9, 10, 11, 12 electrons. So one more electron goes in one of the 3p orbitals, so we end it with 3p1. So it's really just a list of increasing energy from left to right of where the electrons are. So let's take a look at an example. If we were to look at writing the electron configuration for oxygen, oxygen has 8 electrons. So its electron configuration 1s with 2 electrons, and then 2s with 2 electrons, and then 2p, and there's 4 electrons in 2p's. A good way to check this is you can take a look and go, okay, I have 4, 2, and 2. Do they add up to 8? Yes, they do. So it means that my electron configuration is probably right. One more example. Let's do calcium. So calcium has 20 electrons. So let's start filling. We'll go 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Okay, so we're just going in order of increasing energy levels. Now, if we had a transition element next, then we list our 3ds up to 10, and then we go into our 4p's from there, and so on and so forth. Okay, but calcium is just up to 4s2. Now, what's really neat about the periodic table is you can get these electron configurations just by taking a look at it. So electrons or atoms that have electrons that end in either group 1 or group 2 are called the s block. And so these all end in s electrons. Our transition elements all end in d blocks or d orbitals. So we call that the d block. And atoms that are in this section of the periodic table are in the p block. So they have electron configurations that end in p orbitals. And then the lanthanides and actinides are all part of the f block, and they have electron configurations that end with f orbitals. So what you could do is say we want element number 28 here, which is nickel. And we wanted to get the electron configuration. Well, we can read it right from the periodic table, and we're going to kind of read left to right across each row. So we have 1s2, and then we've got 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and so that's how I quickly get an electron configuration, is I'm just reading them from left to right. And what's really nice about this is you get the weird jumps then when you get down to, from 56, the 4s2, Then it goes down here to 4F14. And then it goes back into 5D10 and then 6P6. So like it's a nice way to get those really, really weird electron configurations. You can also write shorthand electron configurations. So essentially what you're doing is you're taking the core of the electrons and stating them as the preceding noble gas because noble gases are stable. So for example, if we had full electron configuration of neon, we got 1s2, 2s2, 2p6. Okay. If we look at magnesium and write the full one out, we're going to go 1s2, 2s2, 2p6, 3s2. So the shorthand configuration basically takes this preceding noble gas of neon, and instead of writing out 1s2, 2s2, 2p6, we can write just neon in square brackets followed by 3s2. And that would be the shorthand notation. Similarly, if we've got sulfur and we do the full one, it's 1s2, 2s2, 2p6, 3s2, and then 3p4. Okay, again, here's our preceding noble gas. So the shorthand for this would just be neon, followed by 3s2, 3p4. Now, there are two exceptions to this rule, and they're just essentially kind of unique. One of them is chromium and one of them is copper. So let's write out and do chromium first. So chromium is 1s2, 2s2, 2p6, 3s2, 3p6, and then normally we'd go 4s2 and then we go 3d4. Okay, but it's actually a bit more energetically favorable to half fill all the d orbitals and keep this s orbital half filled, mostly because they're really close in terms of energy. So it is a little bit more energetically favorable. So instead of writing 4 here, we would write 5, and instead of writing 2 here, we'd write 1. So its configuration would be 4s1, 3d5. Copper is very similar. So we got 1s2, 2s2, 2p6, 3s2, 3p6, and then if we were doing it based on the rules, we go 4s2 and then 3d9. But again, it's better to completely fill the d's and only half fill the 4. It's a little bit more energetically favorable. So its actual electron configuration ends in 4s1 and 3d10. Those are the only two exceptions you need to know, but you do need to know those for our course. Now, finally, let's take a look at writing the shorthand electron configuration for the iron 2 ion. So this is an iron 2+ ion. So we'll start by writing out iron, and then we'll take electrons away. Now, the preceding noble gas here is argon, so I'm going to put that in. And then from there, we have 4s2. And then we've got 3d, 1, 2, 3, 4, 5, 6. Okay. Now, these are kind of interesting because our rules say when we create cations, we have to take the electrons from the orbitals that have the highest principal quantum number or the highest energy level. Looking at this, the 4 is bigger than the 3. So that means the electrons actually come from the 4s before they will come from the 3d. So this particular ion is going to be argon, and then we don't even write the 4s's, we just write 3d6. Okay, so it's a little trick for you. They come out of the 4s first before they come out of the 3d. Finally, if we want to go for the full electron configuration for the copper 2 ion, let's go and write it for the full just copper first. So 3s2, 3p6, and then we got, remember this is the weird one, so 4s1, 3d10. Okay. Now a copper 2 ion means copper 2+, so we need to remove 2 electrons. We're going to take one from the 4s first, so that's going to go. And then we're going to take one from now the 3Ds, because that is now our next highest. So it's going to end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d9 for the copper 2+ ion. That's it for this video. Let's move on to our next task.